Welcome to the viewers. Now we discuss an idea of topology, interesting nature, in the form of the theorem. A subset H in topological space x tau is closed if and only if, that is necessary and sufficient condition, if its complement x minus h is open in x, that is x minus h that belonging to tau, where tau is the topology. Then how to prove it? This is a part of solution. Let us consider H be a closed set in x tau, where x tau is the topological space, we know. Case 1, if H is equal to phi, that is H is empty set, then H is closed, so x minus h, its complement of h, is open set. So already we prove its complement, so the result is trivially true. Now case 2, if h is not equals to phi, that means h is non-empty set. And let us consider, since h is non-empty, so there must be some point and h is non-empty, and so x minus h is also non-empty. And let us consider, suppose v be the element that is in the position of x minus h. As h is closed, so x minus h is open, then v is not the limit point of h. It is clear. Since v is the element of this x minus h position, if it is the topological space in x, if that is the element, that's a closed h, and h is a closed, certainly this is a part of x minus h, that all the part of open, it is a closed set. So x minus h is open. certainly if V be any point is there, suppose, so here is the point of V, so V is not the limit point of this, so certainly V is the element of x minus h, that is the element of open set. So certainly V is the neighborhood point or intermediate point, not limit point of h. We find ANBD of V, say NV. Certainly we find NV if we take as NV neighborhood point, such that this NV, this neighborhood point, and this H are never meet. Clear from the diagram. This is the part of NV and this is the part of H. They are not met. They disjoint. If we find, suppose they disjoint, so clearly this is phi, which shows this NV is included in x minus h. It is clear from the diagram. And this x minus h contain a NBD of V. It is also clear. So x minus h becomes NBD of each of its points, and it is the definition of the open set. Since x minus h is the NBD of each of its points, like the point containing here V, so V is arbitrary and x minus h containing each of its points. So x minus h is an open set. It is by definition, and this open set in X. It is part of necessary, because here we consider the cases, the subset of the topological space. We consider the subset H is closed. Here we consider closed set, and two cases arises. First one is empty. Then by convention, if we taking H as closed, then by convention x minus h complement of this set. Certainly by De Morgan's law it is open set, and its complement by De Morgan's law, and it is open set. The result is trivially 2. Then we considering the non-empty cases. We already proved these cases. That's also open set. So it is a necessary part. And next we take sufficient. Now the cases of sufficient part. And here in this cases, suppose x minus h is open in X, and if possible let y is a limit point of h. We take x minus is open in x, we consider already reverse cases, and if possible we take that y is a limit point in h. Also, if x does not belongs to h, if possible, also if x is does not belongs to h, then this x belongs to x minus h zone. Obviously, if it does not belongs to h, then x belongs to this, because we already know limit point may not lie in the set. That's why we take the limit point. Okay, here we take the limit point y as a limit point of h, but sometimes it possible limit point may not lie in the set, and we considering this type of case that x does not belongs to h. So where x belongs to? Certainly x belongs to x minus h, but this x minus h is a neighborhood of x. Thus x minus h is a NBD of y. We take here, just we take the limit point arbitrarily, that's why it is y not x. We take here y, so it is a neighborhood of y, and x y are arbitrarily chosen. No matter for that, where why we take different type of points, maybe that is arbitrarily, absolutely arbitrary. No matter for that, x y z whatever maybe, we take NBD of y in such a way that this x minus h element that intersects it with h element is equal to phi. That means here if we draw another figure once more, this is x and this is h, certainly this is x minus h region, and if we take x be the element, we getting here clearly the neighborhood point. If we take the NBD of x, if we take NBD of y, suppose arbitrarily chosen, so it is NBD of y, it is clear, and this intersecting element of phi, and which contradict to our assumption. So which is a contradiction? As we assume this y is a limit point of h. So it is our contradiction, hence our assumption is wrong. So a, so y must not limit point of h. And which shows that this complement is an open set. Since this is not the limit point of h, so y is the interior point. Interior point of x minus h. We find NBD of y. which shows x minus h is open set in X. So in this way we prove these ideas. We have these points all have taken are arbitrarily chosen x, y, whatever may be the point is, no matter for that, u, v, whatever may be, we take the point. So in this way we prove these results. We end our discussion today. If you like this video, like it, share it, and don't forget to subscribe the channel. Thanks for watching.